Everyone, welcome back to Lecture 2 of PD1, VLSI Physical Design Engineering Fundamentals. This is David Campbell with Trace-Semi. We're going to be working with you guys today, but our primary instructor is going to be Phil Huang. Phil, are you ready to go?
Yeah. Chào mọi người. Yeah. Cảm ơn Dave. Thì để tôi share cái screen. Mà trước khi share screen thì xin mọi người đổi tên cho đúng cái tên của mình, và nếu học sinh thì để ST trước mặt, phụ giáo thì để TA, mà còn thầy giáo thì để IN for instructor. Xin cảm ơn. Ok, mọi người thấy screen ok chứ? So Dave, is the screen okay? Mọi người thấy cái màn hình được
I see
chưa?
your screen.
Okay. All right. So welcome to lesson number 2, lecture number 2 of the VLSI Physical Design Fundamentals course. Today we'll have a few things. We start off by having some notes on the setup, the Zoom meeting guidelines, the Google Classroom setup, and Google discussion groups. And Dave and Vu will share some information with you. And in the lecture will be divided into two parts. One is the lecture theory, and I will present that, and then after that we'll have a significant amount of time for the lab number 1 by Tian Fang. So Dave and
recording
Vu,
in progress.
Dave and Vu, can you start with some notes on Zoom and Classroom and the group discussion?
Yeah, happy to. I'll start with our Zoom meeting guidelines.
So I can stop sharing if you have something, Dave.
In future classes. I'll put it in the chat. Go ahead and leave this up. For Zoom meeting guidelines, first, all of you just heard the announcement. For internal purposes, the Trace-Semi is going to be recording all of these lectures, but we're not able to let others record the lectures. So I see the desire for that, but we're not going to be able to allow others to record. The second thing is, when everyone joins the classes, please change your name, put a prefix so that it's easier to organize. I'll put part of this in the chat, and I'll repeat it a couple of times, but we'll link in the classroom to this document. Instructors, IN, students, start your name with ST. Teaching assistants and lab assistants, TA, please. Over the course of the last couple of days, we've been creating accounts for our Trace-Semi students and TAs. The reason is that we had some conflicts between the security setup at the different universities. So please check your email if you haven't already created your tracesemi.org email account or login account. Please do so. This is not an email account, although it will be able to redirect email to your personal email, but this will allow you to log into Google Classroom. The students and TAs should have received this if you were on the approved list. Eventually, we're going to lock other people out of the classroom in accordance with our agreements with the other institutions. So please check your email this afternoon or as soon as class is over. Make sure that you're able to log in with your tracesemi.org email account or login account. After that, once we have those accounts set up and completed, we're going to give you access to Google discussion groups for each of the different labs where you're doing your work. We'll have a north, a central, and a south group. You'll receive instructions on these groups, and a welcome to the group, letting you know that which one you're in. Let us know if there's any problem that you have with your group assignment. And finally, and this is in the chat again, for technical support issues, please contact ts.pd1-support@tracemi.org. That's what I have on my portion. Vu, did you have something that you'd like to share?
No, you have to cover everything that we need to ask the student to follow. The other thing that I would like to add that we will record the all of the lecture that we have online.
Okay, so Dave, you want to go over Google Classroom, or you want me to, or?
Sure, I'll do the demonstrate. You want me to demonstrate it? I can bring it up.
Yeah, please. So that just in case students have questions about what they're not familiar with, right?
All right, 1 second. I keep getting up individual requests that are popping in. All right, everyone can see my my monitor.
Yes.
All right, so this is what it looks like coming in as an instructor. Everyone else's view will be very similar, but may have some slight differences. The important thing is that you get into this screen. That means that your Tracemi credentials are working. Across the top here, you'll see classwork. And this is where you're going to go to find course materials that have been released for the students to access and use. In this case, class information will always stay at the top. Additional new class information will be added here. When something has been added, such as lecture slides, information on building a chip, design flow, you'll see those announcements show up over here in the stream. As we work our way through the course, there's going to be 30 different lecture folders with information that will be progressively released to the students. In the class, you should be able to see your fellow students and message your fellow students individually here. And Tracemi is not going to be grading your assignments. So this is here, but it won't be relevant to you. The most important thing is that you go to be able to get into the classwork, see your lecture slides, and the materials that you're going to need to complete your labs. As we moved into the flipped classroom, you're going to be expected more and more to be prepared ahead of time for each class. You're not going to be able to sit and listen to a lecture and complete your lab. You're going to have to prepare by reading the materials, watching the videos that are provided, all of that ahead of time before we get to the lecture to prepare you. If you'll raise your hand or put up any questions that you have in chat, Vu and I will try and get to those. I'm going to go ahead and stop sharing my screen unless Phil, you want to narrate.
Dave, can you show them how to contact the instructors and all? Yeah.
Okay, so my view is different than what they're going to see from the,
okay.
Yeah,
Okay.
It will look similar to this. They'll go to the people's page, and they can go much like emailing a student here, but the student view is different here.
Okay. And you want to mention about the, oh, sorry, go ahead.
For instructors to the lab instructors, they're going to, in the email that they're going to receive this afternoon, welcoming them to each of the different groups. The lab instructors will be in those groups, and they'll be able to contact them easiest through the lab instructors. But we really need the lab instructors to activate their account. The TAs You should have received a reminder note last night. We really need you guys to get in and activate your Trace-Semi account so that we can firm up the way we're communicating with students.
All right, you want to mention the upcoming Google groups so that different groups of students in different regions can communicate with each other, with each other. Yeah.
I mentioned that previously. We're going to have 3 separate
Oh,
groups for each of the labs, but some folks are coming and going. When once you've activated your student Trace-Semi account, you should later a couple of hours later, you should be receiving a welcome to the group that you're associated with based on your application, north, central, or south. And you'll receive instructions, a welcome to the group, instructions on communicating within the group.
all right. Anything else, Vũ?
No, I don't have anything else to add until you.
I guess, Dave, I can start the lessons.
Yes, sir.
All right. Let me share the screen again. Okay. Let me start by saying it in Vietnamese and make sure that student understands fully. Thì mọi người cũng thấy là trên cái lớp học là tôi để rất là nhiều tài liệu, vừa cái bài giảng mà vừa cái tài liệu về lab, để coi cái classwork thì khi quý vị vào thì nó có lecture 1. Lecture 1 thì mình có những cái tài liệu như vậy, và lecture 2 cũng có những tài liệu như vậy. Thì cũng xin ghi chú là cái này là vì là mình làm trễ, rất là trễ, thành thử không có bắt buộc là phải là mình phải coi hết, và có một số cái này là như là ôn tập vậy, ví dụ như là cell delays, circuit delays, mấy cái này là mọi người đều là phải biết trước khi vào. Nhưng mà để lại đây là mà có quên á, thì mình có thể có một cái tài liệu mình ôn lại rất là nhanh để mình đủ để mình hiểu. Thì lý tưởng ra là những cái này sẽ chia sẻ tối thiểu một tuần trước khi đó, để cho học viên có thể có thời gian mà xem hoặc đọc và nghiên cứu trước, và sau đó là làm một số bài gọi là assessment để cho giảng viên trước khi vào lớp là biết là cần học viên đã hiểu hết những cái gì, và cần những gì không hiểu, chưa hiểu thì mình sẽ dạy trong lớp thôi. Trong lớp mình chỉ chú trọng là thực tập nhiều. Thì vì mình làm trễ thành thử mình từ từ mình mới làm, nhưng mà cứ để vào đây thì học viên xem được cái nào thì tốt cái đó, nhưng mà từ từ sẽ là gọi là catch up. Nhưng mà hy vọng là tới lecture số 4 có thể là mình chuyển qua cái flip classroom một cách hoàn toàn. Xin hết. Nếu có gì câu hỏi thì xin vui lòng hỏi, giơ tay hoặc là viết trong chat, thì có phụ giảng sẽ cho tôi biết và có thể là trả lời trong cái lớp được. Nhưng mà cái lớp này mình muốn là coi như gọi là rất là sôi động, tức là phải đi qua đi lại. Thì cái lớp đầu tiên là tại vì cái chương trình nó không phải là flip classroom thì mình không có tương tác nhiều, nhưng mà nếu mà được thì mình cần tương tác rất nhiều. Thì hôm nay sẽ bắt đầu tương tác. So Dave, did you have a chance to enter the questions for the Zoom? Because I'm going to start with it.
Yes. 1 second. Let me.
Okay, so we're going to start with the questions. And the purpose of this question is that to see how familiar you are with different topics, right? Just to gauge, or if majority of people already understand the answer to certain questions, then we're not going to cover it. But if not, then we're going to target covering it. At the end, hopefully, by lesson number 4, we don't have to cover a lot of stuff in class, but go directly to the hands-on, and go directly to labs, and just work together in class time. So Dave, let me know if you're ready, or Actually, I should not do this. So Dave, you're gonna set a poll. Yeah. So mọi người, you guys going to have a poll and try to answer questions, right? And hopefully Dave can share the results of how many answer A, B, or C, or D. Try your best, and just an assessment right now.
All right, the poll should have popped up as a window for everyone.
I don't see poll yet. Does anyone see the poll?
Yes, I do see it.
Yes.
I'm not sure if people know how to enter the answer though.
I think Dave would be able to see the answers as they come.
Yes, I'm seeing poll results. We've only had a couple of participants answer anything.
Mọi người xin vui lòng trả lời, tại vì càng nhiều càng tốt để cho mình biết cái lớp như thế nào.
Okay, participation is starting to go up.
Somehow I don't see my poll.
I believe it's because
maybe because I'm sharing. Maybe
you're sharing.
Yeah.
Because you're the teacher.
Okay. How many you have so far, Dave?
It looks like the students, about 21 students have completed the poll.
Okay. Yeah.
Out of 83 that are in the class so far.
Yeah.
83
mọi người giơ tay lên nếu mà là không có trả lời được, để cho biết không biết có chờ hay không. Vâng. Chắc maybe we have a time limit, Dave. So we
yes, the timer is going. The timer
Okay.
is going. We've got 1 minute left on the poll.
Okay.
All right, about 10 seconds left, everyone. Sorry, I was speaking while muted. Phil, it's going to be easier if I share my screen.
Yeah, go ahead. But you share the screen from now. You just, yeah.
I believe. All right, you should be able to see the screen now.
Okay, so yep, there are 28 people got 55% got it right, and 20% A or C. Yeah. So A is not really correct because if state is not an level of abstraction, but overall it's great. Okay. And Dave, can we maybe I'm sorry. I thought it is one question at a time. So that's good. Okay. All right, great. I was worried about the time it takes. Okay. So yeah, what are the different levels of abstractions in a design? So let me okay. So and then second, what are the different tasks in back-end design? Synthesis, place around, sign off, RTL, circuit design, layout, circuit design, extraction, layout, place around, circuit design, layout. So I think the correct question is the first one, synthesis, place around, and sign off. RTL is not back end. RTL is front end. The second answer. The third answer really circuit design, extraction, layout is not a major tasks in backend design, and place around, circuit design, layout, the same thing. So the main part of physical design backend is physical synthesis, place around, and sign off. That's after logical design. Okay. 3, the following are input to place around, gate netlist, cell abstract, timing constraints, physical constraints, and yeah, that looks like the correct answer. RTL is not the input to the place around, and what is that choice output functional design? Okay, all right. So so the correct answer is number 1. Question number 4, what are the primary goals of the physical design? Yeah, so EDA tool is not a primary goal. Modular, hierarchical, regularity are really principles, not the goals of physical design. Performance, power area is the correct answer. So majority of you got it right. What is cell delay? So the correct answer will be a function of input lose and output transition time. So the correct answer is A. So we're going to go over that. Net delay, the same as wire delay, which is correct. Is called by the resistance and capacitance of the interconnect, which is correct. A and B, none of the above. So the correct answer is A and B, right? So, okay, let's go down.
That's all of our class.
Oh, there's a second page. There's some
I was not able
7 to 12.
Yeah,
okay, that's fine. Okay, so I'm going to just go over it in class here. So maybe people can just type in the chat on the answering, but let me share the screen. Okay, the second part is how do we check if the design meets all the performance goals? A, run dynamic timing optimization. B, perform static timing operations. C, run static timing analysis. D, run circuit simulations. Please type in your answer. And then TAs will tell me majority of. All right. The correct answer is C, run static timing analysis, because that's the very sure way of ensuring that all the timing are met. Performance really means timing. Yeah, it could mean power and everything, but the majority of them is just timing. Right. Number 8, what are the different components of a clock definition in the SDC file? Frequency, functionality, duty cycle. B, period, uncertainty, latency. C, edges, duty cycle, setup time. D, all of the above. Okay. So the correct answer is period, uncertainty, latency. B, frequency functionality is not part of a component of a clock. Edges, duty cycle, setup time is not a component of a clock. All of the above certainly is not correct. So TA is how many percent or a lot of people get the correct answer or no?
The students aren't really jumping in with the chat on answering the questions. So students know that you're not being held accountable for this. We want to get a feel for the information and where you are with the material. So don't be reluctant to share an answer that you're not.
Yeah, so if you don't answer, that means that you want to be yeah, we could go over it. Understandable, because we haven't started all these things. But since these things, a lot of things should be already covered in your prerequisite. So that means that if you're not familiar with it, we're gonna cover them. Okay, so number 9, a setup time constraint is the minimum delay time of a path. B, the time after a clock edge of a flip-flop before data can change. C, the time before clock edge of a flip-flop that the data must arrive by. D, the maximum delay time of a path.
Getting a strong consensus towards C.
C, the time before clock edge of a flip-flop that the data must arrive by. Correct. I'm very impressed. Okay, let's do a 10. A hold time constraint is the minimum delay time of a path, the time after a clock edge of a flip-flop before data can change, time before a clock edge of flop that the data must arrive by. D, maximum delay time of a path.
We're getting a strong consensus towards B. A couple of C's.
Correct. The correct answer is B, the time after clock edge of a flip-flop before the data can change. Very good. Number 11, what does this constraint specify? Set input delay 0.8 dash clock, CLK, get ports A. A, signal A arrives 0.8 nanosecond before clock. B, signal A arrives 0.8 second after clock. C, A must arrive 0.8 nanosecond after clock. D, A must arrive 0.8 nanosecond before clock.
Looks like there's some hesitation on this one, Phil.
Okay, we'll cover that. Number 12, what does this constraint specify? Similarly, but, oh, I'm sorry, this is wrong. Set output delay. Never mind if they don't get it. Okay, that's good. Thanks everyone for participation. So to give you a feel in the future, when we arrive, when we fully implement the flipped class, then you will do all these at the end of your review period before the class, so that we will know how much you know and everything before we start class. Okay. So any question about this kind of process? Okay. Okay, so let's go into some. So we have 30 minutes go by. Okay, so the ASIC development flow. So this is a review, right? So the ASIC development flow involves specs, front end and back end, and it goes from architectural to microarchitecture to RTL to logic synthesis, circuit design if needed, and physical design. So the important thing to know is the level of abstractions. And so conceptually, do you see this thing in the way or no? Okay, maybe. So conceptually, the physical design. So conceptually, the front end and back end involve requirements or specification to the group of RTL designers, and in the process, you need to verify what you create. And then on the back end, you do synthesis, you do physical design, and you do sign off before you send to package fabrication packaging, and you build a chip and you do testing before you delivery. So it's not just designing, but designing and sign off and verification. So so on the sign off and verification, this is just different pieces of things outside of this flow. So on the verification and simulations, things interact and go back and forth between the front end and the back end, but basically divided in two parts. One is the front end simulations verification, and automatic test pattern generations, and FPGA prototyping if needed. And all these orange boxes represent certain important deliverables, data that share between different steps. Just to give you a feel of things, but not meant to be understood, each of them, what it means. But on the related to the backend sign off, these are the typical things that we do: static timing analysis to validate your timing, EMIR analysis for power grid analysis related to IR drop and electromigrations, logic equivalence check to make sure your lower level of abstractions like gate level, transistor level, physical layout really match your behavior, your functional, your front end view, because the final design, the physical of it has to match whatever the logical view. So this is an important step that people go through, and mathematically proven the equivalency of the final layout, therefore chips, with the functionality that been simulated and validated. And then on the performance side, also power analysis, does a chip consume within the power limit? And there are behavior in the timing area that cannot be caused by static, even though static is really the math, the complete timing verification, but it cannot simulate interaction between different timing paths. So there are certain test patterns that need to be run in the dynamic mode. And also, of course, physical verification is the verification of the final physical view to the transistor level netlist, because mathematically transistor level netlist can be compared with the behavior model via different methodology, but physical layout somehow has to be mapped into the transistor. So these are the things that we're not going to learn about, but we know that these are the stuff that we need to do before we tape out. And then after tape out, for sure, is just mass making, fabrication, packaging, validation of silicon, production, qualification before delivering to the final customer. This is an example just to give you the real world implementation of a digital design system. This is an example. This is an example out of Skyworks. This is what I created. But basically, it involved design. Right over here, we call front end is design. For the back end, we call it implementation, because by the time you take the design, even though you do physical design, you do circuit design here, but overall from the top down point of view, we call it implementation. So therefore, sometimes you hear the word digital implementation to represent this physical design part of it. And then the last is a sign off. Let's see. So, okay, so last is a sign off. So oh, if I do this, I can't. Is that somehow? So okay. Okay, so that's a design automation, and part of it. And then you see in here the IP management. So there's another key component of design methodologies, design reuse. All these different low-level components or standard components being designed before we integrate into an SoC, for example. So there's some, and then the infrastructure involved, compute infrastructure, design environment, very standard design environment, the project directory structure, revision control, etc. And on the design automation part, EDA tools like Innoverse, that the tool you learn, and also for each tool you have an EDA flow. So in here, every step you have a tool and you have a flow that just a sequence of commands and steps that you record as scripts to allow you to perform all these functions. So this is an example of different steps, right? And this also is the early version of things that Skyworks. Say you have project workspace, you prepare the reference data that you learn later on what we need to do. So in here, the blue is the EDA tool, and the red are internal flows. So you have bits built-in self-test, you have a flow, a tool, you have synthesis and DFT, design for test, you have the tool, the flow, and all. It's all automated in a system that I describe later. So just to give you a few of what the real world system is, but basically in this class we're going to learn about this place around flow, and this is just a review. So these different steps to implement the different steps. We say the physical design have the following goals. Primary goals: PPA, you already know; reliability, manufacturability, and productivity, you already know. So just a flashback of what we're dealing with. So in order for us to achieve those, there are a few things that fundamentally we want to make sure we understand before you go on and start running things. We need to review the fundamentals concept below. So pretty much the delays and the timing constraints are the things that you need to understand fully before you just run the commands. So just a review, because these things you already supposed to already learn. So delays, basically delays, there are two types of delays: the gate delays and the net delays. So the gate delays, so the gate delays is we have the videos that you can learn, but basically when you transition an input, you don't have immediate response, but there's some physical there that you have a delays through the gate. When you go, the signal will go from 0 to 1. The device going to be discharging the capacitance here, which was sitting at 1, discharging. There's a finite amount of time to discharge to bring the signal from 1 to 0, etc. So the time that the signal travel through a gate is called gate delay, or sometimes it's called cell delay. And then there's another component called net delays. So the yeah. Right. Oops. So yeah, so the net delay is here. So if I zoom in, I cannot draw. Right. Yeah. So the net delay. Yeah. Okay, forget about drawing. So the net delay, the net delay is just delay of the wires. Yeah, for going from one pin to the other, due to the wire capacitance and resistance, you have a net delay. So basically, a delay is go through the gate delay, which is a function of input transition time, and then the output load. And the net delay is just a function of R and C's, right? Of the C of the wires and the C of the gate that the gate is driving. So so it's just key some definitions so that when you analyze the timing, you know. So there are something called propagation delays. A rise propagation delay is the time from input to the rising of the output. Or the fall propagation delays from the input changing to the falling of the output. And the propagation delay of a gate is the average of the two. Right? And then definition of rise and fall time is typically just going, the output going from 20 to 80%, and it depends, this number changes depending on the voltage levels. But basically you have a rise time and fall time. Right? So and then this is a little bit more information about delays. So delays really, sometimes your rising input result in a falling, sometimes is rising result in a rising, and they call something called uniqueness, but probably not so important to understand. But basically each of these is called a timing arc. And the cell delays typically measure from 50% to 50% for the numbers, but in reality, sometimes it measures from 80% to of a signal input to 10% of output signal. But basically, when you do all these things, you not worry about the voltage levels, but you will see all the numbers. So this is just an attempt for you to just review what they are. And here, just describe the cell delay. So cell delays basically have three components. Intrinsic delay is the delay of the gate when you don't have any input. When your input slew rate is 0, meaning an ideal signal going in, which means that your delay is the fastest, and when your output is 0, meaning that this is what you call intrinsic delay, when you have ideal input in and no load. And then the other components will be due to the input transition. The slower it is, the more delays you add to it. So that's the input components of it. And then the output components, of the more load you have, the more delays. So this is cell delays include all these three components. Okay, and But you're going to learn more on this. This is the introduction so that you're familiar with all the terminology. And the gate delays also, cell and gate are the same here. So, and there's more information. Wire delays is usually just the same unitness, meaning that rising will cause rising because there's no signal changes here, just from the output pin to an input pin of the next one is called net delays. So it's 50 to 50% as well. So, and then another key concept will be timing constraints. Timing constraints. So most of the digital system are synchronous, right? Synchronous, that means they constructed with sequential elements. And so sequential elements is like you will see you see in the digital design, sometimes you have latches and flip-flops, but in modern design you only see flip-flops. So flip-flops are register. So so a register is an element, a component, a digital circuit that store the data. It's temporarily store the data for fast processing. Yeah, it's just some review of the registers. So the register have the three critical timing parameters: the TCQ, the clock to Q, clock to output, and it's essentially due to the nature of the register, the path start with the clock rising. And then the clock rising have trigger a signal change on the output depending on the input. So the clock to Q, and then the delay through this combinational logic, and then it goes to the input of the next flop. So there's something called setup time. That required we'll go over what the setup time is. So you guys already know, right? And then there's a hold time. So those are the key concepts. So that we need to review to make sure we understand them all. So how do we know a design is fast enough? Well, we run static timing analysis. So static timing analysis. The word static means that you don't rely on vectors or input patterns. It's all mathematical based. So you guarantee that all the functionalities are checked. All the timing paths are checked. There's no need to have any vector, right? So in here. But so the disadvantage of that is that you have to make sure that your timing constraints are complete, because if you don't have complete or correct timing constraints, your result won't be reliable, meaning that you put in the constraints that are not valid, then you have a clean design, but in reality is your design, your layout, your circuit won't perform in real life. So it's very important for checking the quality of the constraints going in. And while we said it is the most complete, but like I mentioned, there are different behavior that need to be checked by, say, dynamic simulations and all the asynchronous glitches and everything that we need to verify in a tool called CDC cross-domain checking and RDC reset domain checking. But you're not going to worry about that in this basic class. But the timing constraints start with so you know how fast the chip have to operate. Then you need to you want to check that. Then you need to define a clock. So a clock means what is a period, the frequency of the system that you need to check. So these are the different definition of a clocks, and this is basic, so you can review later for the sake of time, because I want to make sure I cover this within an hour. And so you learn how to create a clock using a command, and the clock usually have a period, and the duty cycle usually is 50%. So you specify the start and the rising edge and the falling edge, but sometimes the duty cycle is different than 50%. So you use this create clock command to specify your clock, and you learn for most design, the duty cycle is not important until you mix edges. So you have positive edge of flops and negative edge of flops, then the duty cycle becomes important in terms of timing closure. And also on the clocks that you have dividers or multipliers. So you have a base clock, and you generate a divide by 2 clock, for example, by going through a flip-flop. Then you use this command called create generated clocks. These things will be covered in the lab, and it will cover later in different places. So this is just an introduction, so you know what kind of components you will be looking at. And on clocks, you deal with clock skews, meaning in real life, all the delays through all these gates are vary depending on your circuit, because physics. So the temperature, the process variation, everything that will guarantee that you have different arrival time, even though you have one source clock and you have the same number of buffers going to 2 different clocks. You're still going to have a variation in some arrival time. So the difference between the minimum arrival time and the maximum arrival time is called skews. So just know that. And then also, you will learn the concept of uncertainty of a clock. Uncertainty is a way for you to, in timing analysis, to model the differences and skews. And also, if your clock is generated by an on-chip PLL, a phase lock loop, then the actual rise, actual edges of clock, due to the operating conditions, you will not have the same edge all the time. So you have at one point one time delay, and another one is different time delays called jitter. Right, so you use clock uncertainty to model skews, and you model clock jitters and any other margin that you want to put in your STA to make sure that you cover all the cases. So you see this clock uncertainty, and then you'll see the clock latency. Latency is like arrival time of the clock, or sometimes you hear the word insertion time, right? So if you have a source clock at time 0, and it goes through the system, and then it arrives in your chip, and then inside the chip it goes through a ton of buffers. So you hear the word network latency versus source latency. The source latency, this is your chip, and outside of that chip is a system. The clock might be generated from another part of your board, and it takes a few nanoseconds to get to your pin. So when you define your timing in here, you will define your arrival time of the clock by saying there's a network latency. And the latency on the input here is a way for you to, when you don't have a clock trees, you learn how to build the clock trees and how you model the clock trees before the clock trees are built. So in synthesis and placement, you don't have clock trees yet. So you have to estimate the latency. In some cases is important. So you will set the clock latency, and the clock latency will be ignored after you have a clocks built and the actual delays are calculated. So you will learn how this works. But you hear the word network and source latency. And you, the most important thing are the setup and hold time. So just a review, right? So the to the clock of a flop, there always a time requirement that the signal to arrive before certain setup time, so that when the clock rises for the positive edge flip-flop, the data will be sampled. So the data we sample, the data have to be stable before you sample it. If you don't, it's too close, and you enter something called method stability, and you can Google it and learn about it. But basically, the maximum delays of a data path have to be, small enough to arrive, to make sure your signal arrive a certain time called setup time before the rising of a clock. So this is automatically built in your IPs and your cells. So it is something that is a major part of your timing sign off by having this check enabled. And then on the whole time is after you sample the clock, sample the data, right? It has to stay a certain minimum amount of time before changing. Obviously, while you're sampling, your data change will create some problems. So this is what you call hold, right? Giữ nó lại, hold, don't change, right? Before the setup, do it before. So those are the things. If you do it, see over here, you clock edge, and your data changed before this whole time, then this is bad. This is what we call violation. Right? So so basically, setup and hold really are two corners. One is for the max delay corner, and one is min delay corner. And this will become obvious when you go through a couple of STA, and So basically, because when you have a requirement that the signal have to be fast enough to arrive before the clock edge, that means that the maximum the maximum delay would have to be before, because obviously if it is smaller than this maximum delay, then you don't have a problem. But on the whole requirement, since it say don't change too fast, but if your signal is changed too fast, then it's a problem. And you learn it is during the same clock cycle versus the next clock cycle. But these important things that you need to understand when you look at whole time check, it is not the next clock cycle, but the same clock cycle. So all that put together is that when you have a circuitry, right? So all these building block flip-flops will have the timing path from clock to queue. Good combinational logic, you have delays and arriving of the next flop, where your next flop have the same clock, but your arrival time here have to be set up before the clock here. So this is one check. So yeah, and then the other check would be no, this is the same check. So the basically your clock period have to be greater than your clock to queue delays plus combinational logic delays plus a setup time. So this is obvious, right? So all these delays is a limit of how fast your chip can operate, represented here. The T has to be greater than these three combined. And because clock to queue, logic and setup assume that there's no differences between the clock rising edge here and rising edge here, but in reality you have skews, and you have jitter, you have process variations. All that will represent in here as a delta skew. So this is what you call uncertainty, and all these variations you have to compensate for. So that will limit your speed as well. And you see here margin meaning that you need to guard band for inaccuracy in your methodology. So you have to add some uncertainty to cover in case you're not accurate in some area. So hold similarly. So I'm not going to go over this. So hold is just it's the same clock edge, and your clock to queue and logic has to be greater than T hold, meaning it cannot be too fast. If too fast, then it violates the hold. right? And then margin and the skew will affect the violations on this kind of checks. So in summary, these are the equations. And in addition to the major setup and hold time constraints, you have what we call the previous setup are covered for register to register path, meaning from the flop to flop. But when you in a system, your input arrival time is not going to be the same for chip to chip. So you have to model your input arrival time with respect to the system clock, and then on the output, you want to model the output have to be fast enough to have a setup time for your flop on the board. So that means you have something called set input delay and set output delay to put the constraints on your input and output. So it's an extension of all the setup and hold check. And
Hey,
also
Phil?
yeah.
We're at 10 o'clock. Did you want to
Okay.
take a 5-minute break now?
Yeah, let me see. I think we're almost done. Okay. All right. Let's check a 5 minute. Yeah. Okay.
All right. I'll put up a timer on the screen for everyone.
All right.
Recording stopped.
We'll return back to class in about 45 seconds.
Hey, Dave, did you finish?
Yeah, ready to start whenever you are.
Okay. Am I still sharing?
You're not sharing yet.
Okay.
Could you
Recording in
record?
progress.
Okay. So you see the screen?
Yes.
All right. So sorry to go over very quickly because I want to transition to the flipped classroom as soon as I can. So these are things just want to get to it, and at the end I want to open up for questions and anything you want to cover in details before we go to the labs with Tim will lead. Okay, so so the IO constraints, so the summary is that you want to model the system level, this yeah, to make sure that you your chip you know can represent the system, whatever the delays going before before coming your chip, and then whatever your requirement is, right? So when you have an output, that output has to be fast enough to be set up to the next next chip. So so that's what you need to worry about. And then in addition, you need to model your board level, say your input, right? So your input, you have arrival time, and you have, when you model the input, the best will be you have a gate that you just use to model, make sure that your driving have a resistance and have a drive capability, so that it will model exactly the rising and falling time on your input. And on your output, your board will have different output loads. So you do this in your constraint files, right? And then and another thing you will see in your constraint will be case analysis, set case analysis. So it is something you use this set case analysis. This set case analysis command, somehow my thing did not work anymore. Okay, so you use set case analysis, and so you set the chip to a certain function in an SDC constraints, because obviously your chip have different mode, like a functional mode, test mode, and scan mode, whatever. So you, in your constraints for each mode, you have a different timing constraint file called SDC. So you will see set case analysis command and all, and then also you you have a constraints on the design that you say your signals on chip cannot exceed certain max transition, meaning transition time, the rise and fall time. It cannot be too slow. The reason for that is that for timing accuracy, if you're too close, too slow or too fast, you outside of your characterization level, characterization range, and your timing delay will not be accurate. You learn about that. It's called extrapolation and interpolation kind of things that you learn. But basically on your input timing constraint, you need to set max transition, max capacitance, and max fan out. So a fan out is one. If you have a gate, I don't know why am I driving my inks, then maybe the ink color. Okay, I cannot draw. So a fan out is if you have a gate and you drive 3 gates, so that's a fan out of 3. So the reason for max fan out is that you don't want your signal to go too many different places that you'll be affected by the R's and C's. Max capacitance the same way. If your signal is too heavily loaded, you will be outside of your characterization windows, and therefore your timing is not going to be accurate. Okay, so and another thing you will learn is that multi-cycle pass. Based on your design, sometimes in normal mode you have a what you call single cycle, where you have the launching the launching of your path in one cycle, and then you capturing it the next cycle. So what rising edge to rising edge. But if your system design, your logic design allow for the data to be weighted for more than one cycles, then you use something called multi-cycle paths. You say, okay, my data can be slow, and my logic will allow for not sampling the data on the next clock edge, but will sample on the following edge. So you just set multi-cycle paths, and you can set more than one, more than 2. You can set multi-cycle path 3, 4, 5, depending on your logic design. And that is for the setup. Typically, because your chip is slow, and for certain part of your circuitry of chip is slow, so you want to be able to meet the speed by specifying multi-cycle paths. But on the whole, when you specify that multi-cycle path, it will affect the whole. But the whole of the effect of multi-cycle paths on the whole is very not straightforward. But for the basic class here, I skip it. Don't try to understand it. And then if you want to understand it, you can just go to the details. But from the conceptual point of view, you don't need to dig deep for the sake of time. So and then another things that you will need to be familiar with is called timing exceptions, false paths. So in it logically, sometimes you have logic inside your design, and by analyzing your timing in the static mode, it doesn't know your logic. It assume anything can happen. But logically in your path, sometimes a certain thing won't happen, won't be possible. For example, in here you have 2 muxes, and you have the same select line. So there are 4 paths. I wish I can draw, but there are 4 paths. Path 1, you go from A to C, C1, C2. So when select is 0, then you go through the 0 path here. So you have 1 path on the top. Path 2 will be A to C, and you go down here when select is Yeah, if this input is 0 and this input is 1, then that's what the path is, right? So you select, your path will go from A to C to the down here to out, and similarly the path from B will be B to C out, or B to going down here. But logically, you can only have either 1 or 0 on the same select signal. So logically, the path from A to down here and B to up here are not possible. So if you count them, then you overkilling it. So if it affects time enclosure, then you do set false path and you false path these paths. So just a way to explain it. And let's see. So another thing you need to understand is something called multi-corner. So basically, in the past, you have one constraint in a corner. For a corner, corner means PVT, process, voltage, and temperature. And then you have different modes, like functional, test mode, scan mode, etc. And then you do one at a time, but the modern tools, they will look at them concurrently, so they have a constraint file that encompasses everything, and so everything is defined, every mode is defined, every corner is defined. So it have a series of command. You will, so for each of the mode or each of the corner, you have a time, what we call timing constraint. It's a different file. Obviously, depending on your mode, you have different requirements. Depending on your corner, you have different requirements, and then you use a series of commands that allows you to build something called analysis view. So those commands.
Just want to tell you that it's 9:18. So
yeah, okay. I'm going to be quick here. So perhaps I'm going to just jump in here. So basically, you create a library set for different process corners, and you create constraint modes for different modes, and you create RC corners for different corners, and combine together into delay corners, and you create something called analysis view. At the end, you say, I'm in functional mode with the maximum delays, and I'm in test mode with the minimum delay, and then you use this for your constraints. And also some concepts of timing derates to model on-chip variation and statistical timing analysis for advanced on-chip variations as something that you learn but won't be covered here. Okay, that's the end. All those things you need to know, and the important thing is for PPARMP is a performance is everything. It's a lot of stuff in performance, so that's a major part of it. So time to time enclosure means that if you have the right methodology, you go through time enclosure very quickly. If you don't have the right methodology, you take months to do it instead of weeks. So it's important to understand the concept and do it correctly. Okay, that's all I have. Do you guys have any questions before we turn over to Tien? Okay, no question, right? Okay, go ahead, Tien.
okay, just give me a minute here. So hello, chào mọi người. Can anybody see? Can you all see my screen?
I can see your screen.
All right, thank you. So thank you, Phil, for going through the lecture. So for my portion, essentially, I'm gonna cover the lab, right? Specifically, we're gonna cover the Cadence Pleasant Route tool, Innovus. So hopefully, you have something to play with all the basic knowledge that you have learned for the lecture 1 and 2. So it's like change of pace, right? Instead of like sitting there listening to all these knowledge, we have something that we can do. So for the lab, this is the agenda. So I'm going to go through how the lab data are structured and introduction to the Cadence Innovus, how we're going to start the tool and get familiar with the GUI or graphical user interface. And finally, how, one of the most important things that when we use a tool, how to get help, right? So if we want to learn about new command, what are the capability of the tool? How do we get access to those? So, and I try to be interactive. So I'm going to try to do the slide and then we can switch back and forth with the interactive here. So hopefully make it a little bit more interesting. So for this PD1 class, so this is how we structure the lab data, right? So as in here, every overlap data going to be under mount trisomy and then labs. And they're gonna, get populated from, let's say, lab 1 to, how many lab that we have. And then as a postfix with what essentially give you a little bit idea of what that lab is about. So let's say in this case, we have lab 1 introduction, right? So we name it like lab 1 intro. And let's say lab 2 going to be we're talking about the import. So it's going to be lab 2 import. So for today, we're going to do lab 1 introduction. And as you can see here, this is the breakdown, right? So I just want to point out the important document here. So we're gonna name it very consistent with the lab itself. So we're gonna call it lab 1 intro PDF. So so let me turn on the pointer. So here, so that's the convention that we're gonna follow. So let's say next lab is gonna be lab 2, and then we can have lab 2, and then import PDF, right? So and so ideally, the lab will be populated, and then the TA should be to help you, copy the data over to your user workspace. So here, some of the command that I recommend the student to do is you go here, and for this lab 1, we're gonna copy the data to your user workspace, so that's something you have to work with the TA to make sure that every student has a unique workspace that they can work with, because I know that we do have to share the account. So work with your TA to create a unique workspace for you. So stop me when you have questions. So for now, I'll just keep going. Okay. So how you actually run the tool, right? It's pretty simple. The tool already installed in the the virtual machine that you have. So you can do a watch command, essentially telling you where it's located, right? And then you can do the inverse command that's stylus. So so traditionally, that's what they call that's a legacy mode, which we do not cover that in this class because it's time to move on with what they call a newer version with a common UI. So in order to invoke the tool in common UI mode, you do the inverse dash stylus, right? So right here, I have it noted here. So so by default, it's gonna create all these inverse.cmd, which stand for command, and then inverse.log, and then inverse.logv. Log v here just verbose, right? So it's the same as the log, but it has additional information in it. So it's you have a script that you already know what to do. You just want to execute certain a series of command. Then these options allow you that option. You just run something and get out, right? You don't have to actually open the tool, and do it interactively. You can do everything in batch mode, right? So these options give you that option, the ability to do that.